Well, I'd been going back and forth trying to identify the source of some power problems I was having with an oscilloscope I was trying to restore. That back and forth is detailed in part one of my Hickok 640 oscillograph restoration video. But for this part, I'm just trying to document my attempt at rebuilding the transformer after I finally came to accept that it had to be faulty. This is an effort I undertook only because the transformer appears to be something of a specialty design, and it would be very unlikely for me to stumble across one online. This is a transformer installed in my Hickok 640 oscillograph, which is a very early version of that scope. The device underwent a number of alterations early on, some of which involved a few slight changes to the transformer. I discussed those changes in part one of this restoration. The transformer has a single primary coil as shown here, providing 110 volts AC from the mains. It's equipped with 5 secondaries as shown here. The red coil provides the high voltage, the yellow coil has a 5-volt potential and provides the B+, the green coil feeds the heater for the CRT, the brown one feeds the heaters on almost every other tube in the scope, and the slate coil feeds the phasing circuit. The high voltage coil can be further subdivided into 2 areas of functionality, where the red portion generates 400 volts on each side of its center tap, and the blue portion of that coil generates extremely high voltages beyond 1000 volts. This distinction surfaces later as a small set of windings generating 1.5 volts potential is physically separated as a unique outer coil. We pick it up after I finally came to accept that it must be bad. Well, I'm back right where I was with this transformer pulled out of the machine. I had it plugged back in, and these 2 leads that you're looking at that I've got tied down, one with that white tie and then the other one with the yellow. I've got them strapped up here to my ohm meter, and you can see I'm reading 1.3 kiloohms. Well, those are 2 different coils. It isn't until I tried to strap both of these leads down to ground that I found out that it's blowing a fuse. In fact, it took me a little while to figure out that that's where it's at because I went through quite a few fuses. This is the actual high voltage center tap, and those other 2 leads with the heat shrink that I put on there, those are the 2 high voltage leads. And this one is the center tap of the one I've been looking at all along. It's the one that has 3.15 volts on either side of the center tap, 6.3 volts total. So I'm going to open it up this time. Last time I didn't even open it up. I just got to the point where I thought, you know what, maybe I'm overthinking this thing, but it looks like there's some sort of an issue, and I'm going to open it up and look inside. Well, I've opened it up and looked inside. I don't really find anything obvious. I may have to get a little bit more creative. And nothing spells creativity quite like a hammer and a chisel, am I right? Actually, I wound up having to resort to this approach because the copper band was just too big a heat sink for my soldering iron to float the solder, and I didn't happen to have a torch on hand. It worked fine, but the copper band would have to be hammered back into shape later. After removing some of the insulation cardboard on one end, I found that the coils were terminated on a nice terminal strip, also fashioned out of cardboard. This bit of organization somehow made the core seem a little less intimidating. But the other end of the core didn't appear to have a similar terminal strip. It looked like the conductors were wrapped within each of the coils. I've torn the transformer mostly apart now, You can see there are the laminations from the core over there, and this is the windings. This is the copper band that I had to chip off with the chisel because my soldering iron wouldn't get hot enough. And those are the cover plates and some of the paper that was used to insulate it. When you get down inside, it actually doesn't look too bad. It makes a lot of sense on this side anyway. What you can see is there's points of termination that come out of the coil. You can see the wires coming out of the coil there. They tie down, and then the leads going out to the world. The layout on this transformer is in the center. You can see these are the primary leads here, the two black ones. They're in the very middle. And if you look where they go under the coil, it's way down to the base of the coil. So the primary looks like it's the innermost part of the coil. And then as you work your way out, this pair is, it actually looks like it's pretty close to the primary, maybe even right after the primary, the second coil out. It's the 25, 50 volt feed. You can see two of the leads here from it, and there was a center tap on it, but I think it's on the other side, on the bottom side here. And then going out from there one more, you can see, what is the outermost one that I've got here? Let me look at the lead. Oh, this is the one that's suspect. This is our coil that we think is shorted with the, and you can see that it is pretty far towards the outside. And it's interesting to note also that the gauge of the wire, ours is the thickest gauge wire of all of those that we see here. If I flip this over, you can see a few more of them on this side, and most of them are associated with an outer coil, except for, I think it's this lead right here. This lead is not associated with an outer coil. It's tied to something that's closer towards the inside right here, coming down here to this lead. That is the center tap for the 50 volt, 25 volt that we looked at on the other side. The two green leads here, these are the 6.3 volts that feed the CRT. This is part of the high voltage coil, but it's the outermost part where it's 900 volts, and what that's used for is to tap to another lead that creates 1.25 volts, and the lead that it taps with is way over here on the other side. Let's see if I can see it up here anywhere. I think it's this one right here. Yeah, it's this one, this frayed one. This outer one here, I think is 5 volts. On this side, it seems like what they did is they put them side by side, and you know how they had them farther apart. Here they've got the two side by side, and it's an outer one as well, outer coil. This side makes a lot of sense. You can kind of look at it and figure out how it's all wired. You have the innermost one is the primary, and then on top of that you have the little 50 volt / 25 volt leads. I think that feeds the phasing circuit and then goes out and does a whole bunch of other stuff. And then you go out beyond that, and that leaves the rest of the high voltage current coil, or that is the high voltage coil, going from about here until you get out here to where these other coils are. So all that stuff in between is for the high voltage coil. Okay, so all of this makes sense, but if I turn this around and look at it on this side, I'm going to turn it on its side like this so that you can actually see what I've got here. There is no termination strip or anything like that. Basically, it's just, you know, the leads pop out of the coils where they are and go out to the world. There is no middle point on this site. For whatever reason, they didn't do it the same way. And what you see that I've torn apart here is, I was hoping against hope that I would find something that was very obviously, you know, at fault, that was causing the problem, and then I would just cover it back up. But unfortunately, that didn't work out. And you can see here that what we're looking at is 4 secondary coils on the outermost part. And we can kind of identify which ones are which, because based on the number of windings, this one we can see there's only 3 windings on this one. It's probably closer to 3 or 4 if we count what's on the other side, right? And there's a website that I went to. It's a great website, and I'll put a link to it in the comments. But you know, they tell you how to calculate the number of windings that you need, and how to calculate the gauge of the wire that you would need for each winding. So I just do that in reverse and say, oh, okay, I'm seeing 3 to 4 windings here. That's got to be my lowest 1.25 volts. And basically, what they said, yeah, that's about right, 1.25 volts, because you take a look at the area here. Here, let me do this like this. Maybe it'll make sense. Huh, looks like it's somebody's initials are on there or something. I'm not sure. That could just be some sort of stain. I don't know. But anyway, you multiply this by this, and you're able to come up with a volume space, and that will tell you how many windings you have to have for each volt. And I looked it up. They have a nice table on that website, and basically what it tells me is that for this volume, I measured it. It was 1.1 inches by, I think it was 2 inches. And that came out, when I convert that to centimeters, to be a volume that would support 196 to 200 watts, something in that territory. And it's 3 windings per volt, okay? Which means that on the innermost winding, where our primary is, you'd need 360 windings. If it's 115, then you go down to 345 windings, etc. In order to get the 900 volt winding, you got to do 2,700 turns. So that would be crazy to have to redo that. That's, wow, that'd be a lot of work. And I don't know if I could get it into the space that this is in. But anyway, returning back to this, we can assume that the 3 windings that we see on this coil right here, 3 to 4 windings, is probably our 1.25 volts. Now for the other 2, it's very hard for me to count the number of windings here and the number of windings here, but the gauge is directly related to the number of amps that each one of these coils consumes. So I went through on the back of this same sheet that I took all of my measurements on, and I kind of looked in the drawings, and then to come up with a number of all of the tubes, so I could kind of rough out how many amps each one of these would take. And it's obvious that our coil, which is coil number 4, consumes 4.9 amps, because it has all of this that it feeds, which are 4 12AU7s, 4 12AT7s. It's got a 16J6, a 6C4, and an 884, and 2 6AG7s. And so I wrote down the amps for each one of those and added that up, and it comes up to about 5 amps. If I look at the other coils, coil 2, which is the 5 volt, that's the 5 volt. Where does that go? Oh yeah, I got it marked there. It goes to the 5YG tube. And then that's 2 amps. And the 1B3 has 0.2 amps. and the 5UP, which is the CRT, has 0.6 amps. And the way that I found out what all those numbers are is that there's a great website, I think it's Fred's tube data or whatever, Frank's tube data, and it's just a wealth of information, it really is. But anyway, I was able to tally up what each one of these coils would consume based only on the tubes that they supported. And most of them just support the heaters on the tubes. So that means that this one off to the left that we're looking at, that biggest gauge one, that's got to be our coil, the X heater coil. Then you have these two coils, which one is which? Well, we know that this one, this little one is the 1.25. We've already figured that out. So that's the one that supports the 1B3, 0.2 amps. Look at the other two. Well, coil 2 is 2 amps and coil 3 is only 0.6 amps. So whichever one of these, this is a bigger gauge here. So my guess is that's for the 5YG. This is the smaller gauge. That's probably our CRT coil. So, and the 5YG is kind of a hog. It's one tube, rectifier tube, and it, of course, is all high voltage there. So anyway, that's how I arrived at that. And once I tore all of this apart, there's one that's an outermost working to the innermost. So in order for me to go in and look at this particular coil, which is the one we're interested in, this is the one that is shorted with the high voltage coil. In order for me to get there, then I would have to remove, I think this one's the outermost coil, and I can't tell which is, and then this one must be number 2, and then this one is number 3. And then finally you get to this one. So unfortunately, it's not, there's not that many windings on them. I mean, if we figure that it's 3 volts to get the 6.3, how many windings is that? 3 times 6.3, whatever that is, 18, almost 19 turns. And then the 5 volt one would only be 15 turns. So, and then we get back to ours, which probably goes up to, it's probably buried down here a little bit further underneath these other coils, but it goes, that one's going to require, and it's got a center tap as well, but it's, and in fact, that's the wire that you see up here. I haven't identified the wires, and I will, but it would require, what, 18 or 19 turns as well in order to support 6.3, and with a tap in the middle of that, which would be somewhere around, I don't know, 9 turns is where they would bring out the center tap. But this is the center tap for our suspect coil, and this is the center tap for the high voltage coil. These 2 leads here are the high voltage leads. You see that they just sort of pop out of the middle as well. And this wire, I mentioned this one earlier, this one is the other half of that 1.25 volt circuit that's attached to the end of the high voltage coil. But that's, that's pretty much how far I am now. Now I'm just trying to contemplate, tearing into this thing. Well, here I'm starting to tear into that thing by removing the cardboard insulation that covered the first outermost coil. And after removing that outermost coil, here I'm taking a reading with an ohm meter. After removing the 1.5 coil, though, I began to notice tracks of paraffin residue on the cardboard where the wire had been. And here you can see that the residue is really apparent after the third coil was removed. And I was beginning to get the idea that I might not be able to reuse all of the wire. After removing the fourth coil down all the way down to the center tap, the short finally cleared. And although I couldn't see exactly where that short had been, I began planning to rewrap the coils and making sure that nothing shorted along the way. But unfortunately, I would have to wait until I received a shipment of new magnet wire because the insulation was just too far gone on the coils I had removed to consider reusing. Well, after getting two of the windings back on, I was starting to work on the third one when catastrophe struck on this thing. And that is that this wire right here broke off. This black lead right there. And where it's located is right here. Now, although this wire break seemed at the time to be a catastrophe, I would later come to view it as something of a huge stroke of luck, because if it hadn't have been for this break so close to the core, I wouldn't have discovered that a much worse issue had occurred at the same time that the short cleared. As it turned out, the HV coil had also gone open simultaneously to and undetected by me because I was focusing entirely on clearing the short. It now seems that when the short cleared, it also opened up the HV coil. And the wire breaking where it did was a completely incidental occurrence that was unrelated to any of the other issues. I guess it helps to have angels on your shoulders at times. A real catastrophe would have been putting that entire thing back together, only to find that it didn't work. Okay, so I have a worst case scenario. I wound up having to remove all of the coils in order to get down and figure out what the deal is. This is the wire right here that broke. But you can see that this is the coil wire that it's attached to. You might be able to make it out. It's as fine as a hair, if not more. But that is supposed to have about 300 turns and terminating onto either this lead or the other one. I haven't figured out which. I'm gonna have to take a step back because this is as hard as a rock. This is what I would think is probably boiled out paraffin. And I'm trying to make a decision on what I'm gonna do. It just went from bad to worse. This is the broken part of the high voltage coil that we have that I'm kind of looking at. I originally thought it was just 100 volts difference from the rest of the high voltage coil, but as I look at the drawing and look back at, and I'll go over that, but that this coil here is actually 2,700 turns. So it isn't the total high voltage coil is 2,700 turns, it's just the 900 volt part of it, the last leg of it that feeds into the 1B3. Anyway, I found both ends of it. Before I couldn't even find both ends. I don't know if I can get it to focus on it or not, but you can see it sitting on my finger. It's very, very, very fine gauge. I think it's probably 36 gauge wire. And here's the other end of it here. I managed to dig it out. This is what it was tied to before. And I've dug it out and I see where it attaches into the coil and starts going around. And somewhere in the middle of all of that, it's open. And what I'm gonna do is I'll start peeling it back, hoping that it's on the top, because if it's gone open somewhere down here near the bottom, yeah, that's 2,700 turns, man, you know. And if I was to unwind it the whole way and decide to try to wind it back up, I don't think I would be using this gauge wire, which means I wonder if it would even fit within the housing for the transformer by the time it built up, or whether you know, those E's have three legs in them, and one goes in the middle here, and the other two go on the outside. So the question becomes, would it be too fat for that E to be able to even fit inside there if I was to bump it up to say 28 gauge, which is a workable gauge, maybe 32. So the end of this layer is 280 turns. So that means that there's 10 layers to this thing until I get to the other end of it. So I'll take a measurement and keep going. Okay, we are at the very last layer here. I think the last one that I unwound was what, 2360. So we've got, unfortunately my camera battery died at this point, and I wasn't really able to record what I set out to. What it wound up being was that the counter reeled off up to 2,640 turns. That was the size of the coil that I would have to replace, and I set the goal using 30 gauge wire instead of 36 gauge, hoping that I could get at least 140 turns per layer. All right, so I was able to get to 140. Half as many turns as were on this particular coil coming right out of the factory. My goal was to try to turn it showing as little yellow as possible, and you can see places where yellow is poking through, but at the same time I don't want to overlap the wire any at all. So what I've done, the way that I'm doing this, is the tape is put on backwards so that the wire has something to stick to as I'm spinning it, and hopefully I can get it laid in there. When I unwound the original, it was 10 layers. So that means I'll have to do 20 layers, and it kind of worries me a little bit. That's where I'm at. So the next step is to put another layer of tape on backwards on top of this. Each layer wound up taking about 45 minutes to complete. So during one day, I might get 600 or 700 turns completed, taking long breaks in between each layer. That meant it took me about 4 days uninterrupted to complete the entire coil. But by the time I got to, maybe 2,000 turns where we are now in the video, I began to worry that the 30 gauge wire was just taking up too much space and would cause problems. All right, so this is where I'm going to cut it off now at 2660. It's within 40 of what I felt it should be, and within 20 of what I actually pulled off the first time. So kind of right in the middle. So just to take a look, this is it's kind of hard to get the camera to focus in there, but that's the number of layers that I actually lost track of them. I'll go through and figure out how many layers it was by looking at the photographs. I'll be able to figure out how many I had to do, but it's short of 20 because I was able to go from up the number of turns per layer from 140 to 160. As I went along, I got a little bit better at it, but never beyond 160. I think I could get it to 165 if I really pushed it, but 160 is what the average wound up being in both directions. I mean, I have to come up with some way to economize on the amount of space that I'm using here, and I can see that I've taken a ton of it up rebuilding this particular coil. So I'm not even sure it'll fit in there at all yet, but I'll give it a chance and see. And I did give it a chance. I put the laminate around the coil and it fit inside there. However, there wouldn't be enough room for any additional coils. And bear in mind that I still have 4 coils that I needed to put on top of this one. So yeah, there was enough room for this coil to get to fit within the E laminates, but nothing else. So I have to mark this thing off as a complete failure. I went ahead and immediately unwound all the wire off of the core and set it aside and prepared to move on with the next agenda, which would be to order 32 gauge wire and give it one more shot. I've removed the coil that I put on this core, and I'm going to start all over again to put on this 900 volt coil. As you can see here, I did a real neat job of removing the 30 gauge wire. It was just too wide to be able to fit inside here, which is the E laminates. I'm going to have to try a more narrow gauge or a smaller gauge, so I'm stepping down to 32 gauge. And the other thing I think may have been a problem is that I was using this tape, which is a pretty heavy gauge in its own right. So I'm going to switch the type of tape that I'm using to this, which is it's called a polyimide film. It's a very, very, very small gauge. It's just a film thickness, and I'll put that down in between the layers. And I've seen the discussions where people have mentioned that polyimide is not the best tape to use in a transformer because it gets brittle after some period of time. But others disagree and have said that that's not the case. So I'm going to it simply because I'm not going to use it in between coils, but I am going to use it in between the layers of this coil. And I just need something that's thinner than that. I think that's a Mylar type of tape. So I'm going to give this one a shot. I'm going to try the polyimide and 32 gauge wire, see if I can bring the number of layers down to create that 900 volt coil or extension to the high voltage coil. It didn't take long to realize that the polyimide film wasn't going to work out. Not because it wasn't thin enough, but because it was transparent and provided absolutely no contrast between the layers. The thing I hadn't considered was that the yellow tape provided the perfect background to make the small gauge wire visible enough to work with. Without it, there was no way to ensure that I wasn't getting sloppy with my turns and piling them up on top of each other within each layer. So I decided to return to using the yellow tape for the remainder of the coil, which meant the hoped for size reduction would depend entirely on reducing the number of layers, and which itself meant more vigilance to increase the number of turns per layer, with the goal being about 210 to 220 turns per layer. This coil required 13 layers compared to 17 on the previous one. So now the only question is whether the smaller gauge plus 4 fewer layers would be enough. Each coil required 4 12-hour days with several lengthy breaks between each day. Here we watch the last 2 or so turns played out in real time. Okay, that's 2640. So the next step, I'll cut the wire off at this point and then put a thin layer of tape around it just to protect it, what I have right now. And then the first thing I'm going to do is take it off the assembly and check to see if it fits this time. And if it doesn't fit this time, then I'll have to come up with a different plan because I'm I'm not going to go down another gauge and try to make it work. So yeah, we're at 2640. That's it for this one. Okay, this is the coil with the E laminate. Just one of them stuck around the core here. So I've got a little bit of daylight in there to work with. And this is the biggest wire I'll be using. This is 16 gauge. And even with that, there's still quite a bit of room in there. I won't be able to put in much of this stuff though, because it probably would just make it too large. But I do want to be able to reuse some of it, because two of the coils are going to have to be on top of one another. And I'll probably take the two smallest coils, not do it exactly how it was done when I tore it apart, but pretty close. And but the one thing is that I notice that there's a little bit of give in this when I squeeze it. So there is a little bit of room there too. So if I'm able to reuse some of this stuff, maybe I can use this right here on and surround, you know, right where that, right where the laminates are. That would probably provide me with enough so that when I put those E's in there, if it tried to cut in through it, it wouldn't be able to cut through it. It might be able to cut through this paper, but not this hard soak stuff. This is really, really tough stuff. So I would like to be able to get at least one layer of that on the outside. But it looks like I may be able to make this work. Now, for me, the first part of reassembling the core after getting that first coil on is to tie down the high voltage leads and solder them to their coils. Basically, the way it works is that this particular lead here comes in, it's, I guess, what you would call the plus side. It goes through and generates 800 volts, comes out the other end on this lead, which is where we connect our high voltage coil to. This is the center tap for the two. So on each side from this center tap, you should read 400 volts on those two leads there. And then from this lead, it finally goes through the coil over to this. I've got the ohm meter attached on one end to the end of our new coil, and I should be able to get a reading if I attach the other end to the positive side, which means that it would prove it through all the way through the whole thing. And we're reading 649 ohms, so that's pretty good. The next step is to figure out what the next coil is that I want to add on here. But the way that it was put together originally, the bottom coil at this point was the one that was shorted. So maybe I'll just put everything back together the same way that I found it, with the coils working their way outward the same way that they had it. So okay, I've got 3 of the coils on here. 3 of the last secondary coils. I've got a 4th, so total there are 5 coils that I had to put on. High voltage, and then I had to put the one that was shorted, which is this coil right here, and then these two. This is a 5-volt coil, and this is the extension to the high voltage coil, which generates 1.15 volts potential, something like that. I haven't tied up the leads on these coils, but I've got one more to go, and as you can see, I really don't have a place to put it. So what's going to wind up happening, I think, is I'm going to wind up having to put it on top of this. I'm not sure, but I may be able to get away with using 28 gauge wire for this last one. Maybe not. Maybe not. I need to take a look at it to find out. No, I don't think I can. I think I've got to use something a little bit bigger than that, but I got one more to go and hopefully it'll fit. Okay, so the last turn of the last coil. I've cut it off and I have to start working through wiring all of these, but it doesn't appear to be too much wider than the 16 gauge, but it is a little bit. We'll have to see if there's any problems fitting E-lamination over. Maybe I'll take it off there and just give it a trial run right now, just to see how well it works. Well, here it is. I got the E-lamination on it, but it is definitely full up to the gills. And you see daylight there, but it's bumping up against some wires. And fortunately, there's a little bit of play in it. I can squeeze it and it, it has a little give, but I'm going to put some tape around it. And then I think I've got just enough room to fit one layer of one of these things here. And yeah, it's definitely going to need some protection, and I think this will provide it. It's got that really, really hard material right there, so that's really all that's all I'm gonna be able to do is probably one layer. One thing I'll say at the end is that this is a superior product. This one's made by 3M. This one over here is a knockoff. It's supposedly has a lot of the same specs and stuff. And I don't own 3M stock or anything like that, but what does that say? This is 3M 66 tape. Anyway, the specs are supposed to be the same, but this is actually thinner. It's a thinner gauge than this is. And once you put it on something, it sticks. This one will fall off of the anything that's got paraffin on it from this coil. It's on for a little while, but then you'll notice it'll start to dog ear away. That's why I've used so much of this stuff. Finalizing all of this stuff, trying to package it up. So before I can tape this thing up and wrap it in one of these things, I'm going to have to terminate a bunch of these leads. Right now they're just wires hanging, but starting to look a little bit more like a transformer this morning. It's tight. You can see the outer edge of the laminate there is right up against the paper. In fact, it's scraping the paper, cutting into it a little bit. So basically, I've done about the best I can to make sure that everything is pretty well insulated in there, and I've tested the high voltage coil end to end. It's good. I've got a couple of others that I want to go through and start checking to make sure that they're good, because I don't want to get any further in this, because it's not that much to tear this off if I've got to go in there and fix something, but yeah, I need to buzz out the rest of those coils. I haven't done that yet. So. In this image, I'm installing the E-laminates in opposing directions. Each laminate is actually a small bundle of 3 leaves, which is how the transformer was originally constructed. Note that the gaps on alternating sides between each E-laminate is a space for the I-laminates, which are installed after all E's are in place. Here we see an I-laminate laying across the core after all the E-laminates have been installed. In this image, about half of the I-laminates have also been installed, which has a tendency to lock the E's in place. After all of the I's are installed, a pair of shims are hammered into place at one end of the core to tighten the installation up. I got all of the laminates installed. At this point, I'm going to go through and start checking for, um, make sure that none of the coils are shorted together. Basically, I'm going to run this series of tests. This is the one that I used to find out that there was a short between this coil here and this one over here. I shouldn't have been getting any of the readings. These three leads right here are the ones with the suspect coil that we've been working with from the very beginning, and these five are the high voltage, and these five going this way are the high voltage. So we really shouldn't be reading anything in here on 10, 11, and 12. Shouldn't, especially not touching 1 through 5, and these are the readings that I had at first. So I'm going to go through and duplicate that for right now, just to make sure I don't have any leads shorted. I'm not going to bore you with that, but basically I'm going to run through each lead and check it. When I went through and tested all of the coils against one another, I found that, and I did both the ones in the front and the back, I found that none of them were shorted against one another. And within each coil, I saw continuity where I expected to see it. And on the ones that had enough turns for it to be able to differentiate between the center tap and end to end, I did see the difference in ohms when I read it. So everything looks good right now. Excuse me. Now I think what I want to do is go through with my turn ratio analyzer and just verify that the turn ratio and everything is running in the direction that I think that it's supposed to be running. I need to verify all of that before I get down to wiring it. And what I mean by that is that if I can superimpose the drawing on top and I make the assumption, just for a language to choose, that the top of the coil would be the positive end and the bottom of the coil would be the negative end, I want to make sure that the top of all of the secondaries is on the same end as it is on the primaries. So because when I measure it, when I even use this thing, it only works when they're going in the same direction, which means that the coil is rotating in the same way. If I'm attached to the primary, I'm comparing it against one of the secondaries in order to arrive at a turn ratio, what they call a turn ratio. And you can use that math to calculate out the voltage that you would expect to see, or you can use it to say, if you knew the number of turns in the primary, then you would be able to calculate the number of turns in each one of the secondary coils. And that's essentially what we did when we rebuilt this thing. What I've got now is I've got it attached on one side to the primary and on the other side to one of the secondaries. It's the one that's 25 volts from the center tap and 50 volts end to end. Okay. The way this sets up, I've talked about it before. The one with the highest turn count would be the one that you put on the top here, and the one with the lowest expected turn count would be on the bottom. So you put the positives on these colored terminals, and then you tie the negative sides of the two coils together on this black lead in the middle. So that's how you set it up. And I'm just going to turn this on, give it a chance to warm up. Just want to demonstrate how it's done, and then I'll go through and do it for all of the rest. And the reason I'm picking this 25/50 volt coil is because it's fairly close to the primary. The primary is 110 or 120, something in that range. Okay, so right now you use this green eye up here in the corner and the balance wheel over here in the center, and you set it to, right now I've got to set the high, but there's also a low, and I'm going to set it to low for the purposes of this. And you turn the balance wheel and you get an open eye right there. The way that you can tell that it's right is that both the light colored eye and the dark open section overlap. And the closer you can get that, the better off you are. And we have several rings on this dial. The way that you read it, and I'll put arrows, I'll overlay arrows on this, but we are actually on the, showing low battery on this thing. We are actually on the low scale on here, so that's this ring right here. And you can see that the multiplier that we have for it is, it's kind of behind the line here, but it's 4. It's the bottom reading on that second from the center ring. Let me make sure what I'm running. Yeah, so what I'm running from is the center tap to the negative side. So what I'm set up for here right now is reading from the center of the coil to the negative side of the coil. If I wanted to read the entire coil end to end, I could do that. Let me look at that. Yeah, that's S2. If I wanted to read it, how would I do this, right? I would take it from here off of the center tap and move it onto this lead here. Yeah. And what you can see is that the eye closed on there, and we need to readjust it. Let me switch hands here. There's the eye opening again. There it is. And the ratio is now a little, if you look at that number, it's a little over 2. It's between 2 and 3, just barely over 2. So the first one, the ratio was 4-to-1 on the primary to the center tap on the secondary, and it was 2-to-1 this time, going end to end across that same coil. So the first time you can look at it and say, okay, well, we've got 110 to 120 volts, so it's half that. So yeah, it's enough to let you determine which end is which. And from this one test, I can tell which coil is which, and I can tell which is the positive side of the secondary and which is the positive side of the primary. And that's really all I'm going for here, is to just check to see that if it looks like it's set up right to handle the voltages that it was designed to hold. At this point, there are a few revisions I would like to insert into the video that I missed or didn't make clear enough in the original, so that others might avoid some of the pitfalls I encountered. Some of these points were brought up to me after I first released the video, but they seem pertinent enough to warrant this revision. I'd like to stress that each of the coils must be carefully insulated from one another to reduce the possibility of EMS interference. I would have liked to have replaced the original paper back into the assembly, but the same can be accomplished with a thin layer of mylar. One other thing that was brought to my attention is that by this point in the rebuild, you may want to have completed all of your testing, because now would be a good time to soak the coil in an insulating varnish. The varnish seizes the coil wires in place and keeps them from rubbing against one another and causing a short. I had purchased the small bottle on the lower right for that very purpose, but never got around to using it, assuming instead that the many layers of tape would accomplish the same thing. That was probably wrong, and I'll likely have to go back and apply it. I can tell you one thing, though, that this insulating varnish is not cheap. That small bottle cost me about $23 on Amazon. The ad says that the low viscosity of their product allows it to permeate the assembly, and that the resins provide additional dielectric properties. As far as how to do it, I found a few videos on YouTube in Hindi that show the process, and one from the manufacturer. You can also query online discussions where the topic has been discussed in great detail. Personally, I kind of like the syringe approach hinted at by the manufacturer in this picture, but use a manual version that allows you to direct the flow. The person who brought this up to me also suggested that taking it to a machine shop to have it dipped would be the simplest solution, so there are a number of options on how to get the job done. Eventually I would resort to using a clamp and one of those little butane torches to reinstall the copper band. In this image, I'm threading the conductors back through the cardboard insulation that runs between the coil assembly and the outer casing. Those same conductors are then threaded back through the holes in the casing as it is folded on top of the core and reconnected to the laminates. The process is repeated for the other side. At this point, I've put the transformer back together. It's tight. Came in really tight. I'm glad that everything seemed to fit, but it's I'm not going to kid you. This thing was really tight to fit in there. I've got 12 leads poking out on this end, 6 on each hole there, and then there's another 5 over here with 3 on one hole in the bottom of the transformer and 2 on the other. Here's what the bottom of it looks like. I ran new leads for everything. I've gone through and rerun the test that I ran at the very beginning of this thing. It came out pretty good this time. These are measurements against ground. None of the leads were grounded. These over here are all of the secondaries against the primary. And I did compare the primary against ground. I just don't have any place to put it on this. The cluster that you see up here is the high voltage coil. The thing that really stands out that's different is that 10, 11, and 12 are no longer shorted with this coil. If you look at the original measurements that I had, that's what the problem was. There I'm showing 8.5 mega ohms, but it was really 1.4 kiloohms by the time all was said and done. So I'm a little bit happier with the way this turned out. We'll see what happens. The next thing that I need to do before I hook this thing up is to really do a no load test on it and check the voltages to see that we don't have any problems and that we're not blowing fuses anymore. So that's what's next. Okay, I've got the transformer wired through the fuse. It's down here somewhere. And I've got it wired through the switch. And each one of these is the secondaries tied together. There's a high voltage one. There's the 1.5 volt one, but it's on the end of the high voltage coil. That's a 5 volt one there. That's 6.3 volts. And this brown one is our suspect coil that was shorted from the beginning. I have one more tied over here, and that's the 25 volt one, simply because I couldn't tie them all on here. So I'll apply power to this. First thing I want to do is make sure that it doesn't blow a fuse. And I've got a voltmeter set up here so I can take readings. So I'm going to start out. Right now I've got all 3 of the center taps wired together. And that's on my negative side of my meter. Ordinarily, what would happen is that if all 3 of those leads are wired together, the fuse would blow. So we're going to check that right now. I'll apply power to the, see what happens. And I've got the red lead tied off here to the 25 volt because it's one of the 3 that has a center tap. And it's reading 27.5 volts. You're gonna read a little bit more than 25 volts on it because there's no load on it at all right now. I'll move it to the other lead. I'll put the camera over here while I'm doing this. That one's also 27.5 volts. This brown coil right here that you're looking at right there, that was the suspect one. The fact that we're reading voltages right now tells us that it's not shorted, at least. This is reading 3.4, 3.5. It's a little bit higher than what you would expect to see. The other side is also 3.5 volts. That's reading from the center tap, so both of those look good. And then the only other one that's got a center tap in it is this high voltage one up here. And let me see what that's reading. It's 440 volts from the center tap. If I can get it to stay on there. It's hard to do and look over there and try to be safe about this, but that one's 440 volts. So both of them read that. I'm going to shut the power off of this thing right now. The next thing to do is to check each one of these coils separately. I can't measure this this high voltage one, the blue one that you see there. That's the one that is the one that I had to wrap 2700 on. I can't really measure that from there because my meter it'll burn out if I try to. It'll be at least 900 volts if I was to read it from that lead, and it would be 1300 volts if I tried to read it from ground over here. So really all I can do is measure the potential across that coil. So I'll take and attach one side of it there. Now this should measure about 1.5 volts or something like that. And remember, this is, that's about right. I'll have to look at the drawing. But it's measuring 1.3. What else can I measure here and do it safely? This one would be interesting to measure across right here, this green one. That's for the CRT. It should be about 6.5, somewhere in that area. 7.1 with no load. If we measure across our suspect coil, and I gotta be careful. We're getting close to the same thing. 7.0. So we're bypassing the center tap on that reading. We can read across here too, just to see what it reads. Should read 50 volts, something like that. 54, huh? 55 volts. Yeah, probably be a little bit different with a load on it. I have one more coil to check. That's this one, and I don't think I left enough. Doesn't look like I left enough wire on there to really do this right. But this one should be 5 volts. Looks like we're getting 5.5. So this thing really does check out as far as the no load test is concerned. I'm pretty happy with that. The next step on this would probably be I'm going to pull out the choke and just check it to make sure that it isn't shorted. Let me turn off the power to this thing. Okay. So, you know, none of this stuff is wired in yet. I've just sort of got leads strung out so that I'm able to put 115 volts on it and check it that way. So it looks like for the most part this thing is working pretty good right now. But the next step, I'm gonna check the choke, make sure that it's not shorted, and if it's not, then I'm gonna go ahead and do what I can to tighten this thing down a little bit more, and then install it back in the oscilloscope.